used to be 2.7. This is now 2.8, just one-to-one functions in compression. So we defined what a function was, as a function has, if it has a single input, um, for every individual input, it'll have a unique output. So I can say that. But two inputs could have the same output. Well, one-to-one function, it says for every individual input, it has unique output. So if if the outputs are different, the inputs were different, right? And since it's a function, um, since it's a function, if the so I can say if the outputs are different, the inputs were different, and if it's a function, if I have different inputs, um, if I have the same one out input gives to a singular output. Anyways, let me just draw some diagrams before I get you lost on what I'm saying. All right, so here a function is one-to-one. We'll take elements. So here, draw an arrow graph diagram. And so this is a one-to-one function. It takes one element from the domain, sends it to one element in um, the codomain, right? And so, and for every element in the codomain or the range, there's only one element that got sent to it. Something that's not one-to-one, at least for the arrow diagram, is here you have two elements that get sent to the same domain. I mean, you could have something unique get sent to something unique, but the second you have two elements that get sent to the same thing, it's not one-to-one. And you could have like, let's draw this. So you could have three elements go to one. That also breaks it as long as there's more than one. So this is not one-to-one. And we sometimes write one-to-one this way. Okay. All right, and so the point of a one-to-one function is it allows for inverses. And I'll kind of explain why in a second, but let's just talk about, so one-to-one means if I have unique, um, nothing gets sent, nothing gets sent, so I can say this correctly. Man, I just can't put words together that make me happy. Because it's hard to say something, it's easy to say something that's correct. It's hard to say something that it's not misunderstood. Does that make sense? So the one-to-one function just means if you have different, if you, nothing gets sent to the same element. So if if one of the y values is 2, none of the other y values for or your function value is 2. If one of the function values is 3, that means none of the other function values are 3. Okay. So the second you have one of your function values be something, none of the other function values can be that. And if you have two function values which are the same for different inputs, that breaks the one-to-one nature. And the reason we care about this is it allows us to do define inverses for functions, which are super useful. So let's kind of show you how to do this. So we do the horizontal line test. So we do a vertical line test, tells if it's a function. The horizontal line test will tell us if it is one-to-one. And let me kind of show you how to do that. So here, given this function, I guess I didn't draw myself little lines, right? Let me draw the function in a different color. So in fact, let me draw all my functions all at once. So here, this is x cubed, this is x squared, this is x squared, where x is strictly greater than 0, or greater than or equal to 0. And then here we have 3x plus 4, so it'll be up 4. And a kind of a steep zoom. And then we're going to do our test lines in this color. All right, so here you just kind of draw horizontal lines and you just see, oh, yeah, that hits once. Oh, this hits once. This hits once. This is one. So this passes. So this is passes and is 1 to 1. Here for x squared, notice here I hit once, I hit twice. And so this fails. And this is not 1 to 1. And remember, if it's not 1 to 1, this function does not have an inverse. This function, but so what do we do when we usually have something like this? Well, we just restrict our domain, right? And so here, if I restrict our domain, this will now pass. And this is a 1 to 1 function now. Oops. Here, if I have x cubed, and this one here passes. Okay, so this passes. So this is 1 to 1. Notice here this is different than what we use for every input. There's unique output. Yeah, so for every input, there's a unique output, meaning it's different from everyone else's output. That's really what it means. Yeah, that's correct. All right, so here, remember when we did, and here if I did this, this is a test if it's a function. So while this passes as a function, right, because this will pass as a function, it does not pass in the sense of being 1 to 1. So okay, I'll leave that up for a second. All right. So let's talk about an inverse is. So an inverse function. So let f be a 1 to 1 function with a domain A and a range of B. Then the inverse has a domain of B and a range of A defined by f of y of x equals f inverse of y is equal to x whenever f of x is equal to y. For any y in B. And so this function basically puts things back to where you found them. And so I call it, it's like the good librarian. Students come and take all the books off the shelves, and then the librarian comes and puts them exactly where they came from, right? And so let me just kind of show you an arrow diagram of this, and then and I'll go ahead and use like real elements here. So here, let's pretend we have 3 elements here. We'll say we have 1, 2, and 3. And so 1 gets sent to, well, I don't know, 4. 2 gets sent to 9, and 3 gets sent to 7. So here's my function. My inverse function will take those elements, 4, 7, and 9, and put them back. And so I'll take 4, I'll put it back to 1. Here it'll take 7 and put it back to 2. Oh, no. 7 went to 3. And 9 will get put back to 2. Okay. So an inverse just puts everything back. So the nice thing is if I take if f's a 1 to 1 function and this is the inverse fact, it satisfies the cancellation property. So if I take f of x and then take the inverse of that, I get back x. And here if I take the inverse of x and take the function of that, I get x. And this is for every element in the original. So here x is an element of f, and then it gets sent back to, and here x is an element of f inverse. Okay, please note that we write f inverse is this does not equal f of x raised to the 1 over x, or 1 over 1 up to the negative 1 power. The reason we do that because often that I don't know why, it's just often that can cause that to be true, but it's not always true. And so please note that these are two different operations. The inverse is not the function raised to the negative 1 power. Okay. All right, so show that these two functions are inverse of each other. So to show something's an inverse of each other, we do the following. So we just composed f composed of g, aka we're going to show that of x. And so we're going to do this. So here will be f g of x, and that's equal to f of, here we're going to plug in everywhere, g of x here is x to the 1/3 power. And then here we're going to take f to that, so we'll take x to the 1/3 power, and we're going to raise it here now to the 3rd power. Here, if we do this, we get back x. Now this would be true for any element. So if we took 8, let's just take 8 as an example. So here, if I have f of g of x of 8, well, the 1/3 of 8 is f of, whoops, I put an x here when I meant to write a 2 or an 8. G of 8, so 8 to the 1/3 power, or the cubic root of 8, is 2. And 2 cubed is indeed 8. Now let's flip this around. G of f of x. So here you kind of want to show an inverse, you only need to really show one, but it's nice to show both. Just to double check yourself. All right, and then we have f of x, so that'll be x cubed. There we go. And so this will equal x cubed to the 1/3 power. And that's equal to x. Okay. One thing to note real quick, the inverse of x, so f inverse inverse, is just equal to the original function f of x, okay? So the inverse of the inverse is the original function. And that's going to be true for everything you guys do. All right, so that's the end of this page. Let's just take a second. All right, so let's do this last page real quick. So how to find an inverse? Well, to find an inverse, we're going to do the following steps. Let me number them. That way you can see what I'm doing. I'm going to add a 5th step here. We're going to check it. We're going to check it as well. So the first step, we're going to write y equals to f of x, just for simplicity reason, just to have less characters. We're going to switch x and y. So everywhere we see an x, we're going to write a y. Everywhere we see a y, we're going to write an x. We're going to solve the equation for y in terms of x, if possible. Not all inverses turn out to be clean, just possible. And then we're going to write y is equal to f inverse of x, and then we're going to check it. Okay. All right. So let's just do a couple of these. Let me do some formatting stuff. So notice here I left myself a lot of space, and that's because I want to work down. And so I'm going to give myself columns to work in. There we go. And just put a little line right here. So I'm going to work down this way and finish here. I'm going to work down this way and finish here per problem. Okay. That way I can clearly, actually, you know what? Let me make this a dotted line. And this one a dotted line. And this is a solid line. No, it's all lines, so that makes it a little bit more clear what section I'm in. Okay. All right, so let's do this. I'm gonna slowly work through these with you. All right, so yeah, okay, good. I have an example of that. I didn't make sure I didn't. All right, so 1. So here we're just going to write this as y is equal to 4x plus or minus 3. Okay, so the first step, just write it at y. Second step here, we're going to switch x and y. So here we have x equals 4y minus 3. And then we're going to solve it for y. So we're going to start at step 3. So if I was going to solve this for y, x minus 3 equals 4y. And then we'll have y equal, so here up like that, y is equal to x minus 3 over 4. And then here, now that we have even though we write here 4, we'll have f inverse of x is equal to x minus 3 over 4. All right, and then we're just going to check it. And here I like just, and then just an easy, clean way to check it is we'll just type in f of 2. If I plug in 2 here, right, I'll get f of 2 is 4 times 2, which is 8, minus 3, which is equal to 5. So here we want to find f inverse of 5. Does that send us back to 2? Well, f inverse of 5, so we have 5 minus 3, which is 8 divided by 4, which is, oops, 2. Okay, so this checks out. So this is usually how I check it, is I just test the number real quick. You can do composition, but I find if I have that requirement for students to check, they just don't do it, right? Oh, you're right. You're absolutely right. This is a plus. Somehow I'm doing the math correct in my head, but somehow I just left it negative. Sorry, this is a plus. Sorry. Thank you. So I like to have you guys check numbers, because if I want you to do composition and a function, it's just too high of a bar for you guys to check it. But I do want you to at least test the number in your head. And so just pick a number, send it somewhere, and then wherever it sends it, put it back in the inverse function, see if it went back to the original thing. Okay. All right. Thanks for the correction. I really appreciate that. All right. So let's do this again. And so what we're doing here, and the reason why we interchange x and y is because here, if this function takes an x and adds 4 times it by 4 and minuses 3 from it, we want to kind of do that in the opposite order. We want to add 3 to it and then divide by 4, and that'll give us back to where we want. So by switching the x and y's, we kind of trying to write out what do we do to undo what we did. Okay. All right, and so we're going to do the same thing here. So here we'll start with 1. We're going to write as y equals 2x plus 3 over x minus 1. 2, we're going to swap everywhere we see a y, we're going to write an x, and everywhere we see an x, which in this case is 2 spots, we're going to write y. So this is 2y minus, or plus 3, sorry. See if I can keep my things correct today. All right, and then here, 3, we're going to start solving this in terms of the other one. So what I do is I multiply by the y, so I have y minus 1 times x equals 2y plus 3, just to clear out the fraction. And then let's go ahead and distribute the x. So I'll have yx minus x equals 2y plus 3. And then let's move all the y to one side. So I'm going to move this y over here. So I'll have x minus 2. Oops. Let me not skip that step. Xy minus 2y equals x plus 3. Here I can factor out the y, so I get y equals x minus 2 equals x plus 3. Divide out the x plus 3 over x minus 2, and then step 4, we're going to write f inverse of x is equal to x plus 3x minus 2. All right, so let me just be very clear how I solved this. So I took the y minus 1. So I wanted to clear the fraction. So I just cleared the fraction. It's like, okay, so just multiply this across. Once I did that, I went and just distribute this x. And now I want to isolate my y. So how do I do that? I move all my y's to one side and everything that doesn't have a y to the other. So I did that. And then after doing that, I just factored out my y. After factoring out the y, I can just cleanly divide. And here I get my y by myself. Okay. We'll do this again here after doing another problem. All right, so let's do step 5. Let's check it real quick. Let's just pick a random number. Let's pick a number that might end up being less terrible. Hold on, let me pick a number that works out well. If I do... Let's do 2. Yeah, if we do 2, I'm always dividing by 1. Okay, so here I'm going to just do f of 2 again. And the reason I choose f of 2 in this case is if I put 2 here, 2 minus 1 is 1, and so whatever's on top, I won't get a fraction. So 2 minus 1 is 1, and then here I have 2, so 4 plus 3, so that's 7. So f inverse of 7, that look like a 7. F inverse is 7, so we'll have 7 plus 3, which is 10, over 7 minus 2, which is 5, so 10 over 5 is indeed 2. Okay. That's a lot to fit in a small box. Yeah, I probably should have spaced this out a little bit better. All right, let's do the next one. When you write up the notes, I'm okay if you don't write. If you don't have step 5 right there, I'll forgive you because sometimes it's hard to fit it all in the space. All right, so let's do this one. So let's do one again. So I just want, so here we'll have x cubed minus 2 over 6. 2. We're going to swap the x's and our y's. So here it's x equals y cubed minus 2 over 6. Make that look like a 6. Step 3, we're going to start moving stuff over. So I'll have x. So I multiply by the 6. So I'll have 6x. I'll go ahead and move over the 2 equals y cubed. Move that up. And then we just take the cubic root of each side. So the cubic root of 6x plus 2. So step 4 would be y inverse equals the cubic root of 6x plus 2. And so here, let's just test a point again. What point seems good to test? Let's just do 2. Actually, 2 works out great. So f of 2. So here, if we plug f of 2 in here, I get 2 cubed, which is 8 minus 2, which is 6. 6 over 6 is 1. F inverse of 1. So 1 is, so this would be 6 plus 2, which is 8. The cubic root of 8 is indeed 2. All right. All right, let's do this one last one. There we go. And so here we'll have 1. We're just going to write this as y equals x plus 4 over negative 3 minus 5. 2, we're going to swap those two. And the reason we're swapping is because everything we do to x, we want to undo for y. And so by swapping that, we kind of in some way write out what's going on when we undo that. All right, so here we do this again. So what do I do? Same thing we did last time. We're going to clear out the fraction. So I'm going to have minus 3y minus 5 times x equals y plus 4. Distribute that out, so I have minus 3yx minus 5x equals y plus 4. We're going to move everything to one side. So here, minus 3y x minus y. Move the 5x over, so it'll be 5x. Leave the 4 there. All right, factor out my y, so I get my y. Oops, make that y looks like minus 3x minus 1. Remember, this is a negative 1. If I factor out the y, I still have the negative 1 there. And y is equal to 5x plus 4 over minus 3x minus 1. And so we'll do step 4. We'll say f inverse of x is equal to 5x plus 4 over minus 3x minus 1. All right, now let's just test number 5. All right, so 5. Here we're going to just test 2. Does 2 equal something? Okay. Let's just see where 2 sends us, right? We've always done 2. Let's just see where 2 takes us. So here I get 2 plus 4. So up top I'll have a 6. Down below I'll have minus 6 minus 5. Ooh, that seems terrible. That seems awful. So that'll be negative 11th. Inverse of I should pick something that comes out cleaner. Let's pick something that comes out cleaner. You guys don't want to do this. You could, and it gets awful. Let's pick something that comes out clean. So how to pick a good test number. So let's make this down here a 1. So I'm going to pick negative 2 this time. If I pick negative 2 this time, negative 3 times negative 2 is positive 6. Positive 6 minus 5 is 1. And negative 2 plus 4 is 2. So this negative 2 goes to 2. If I plug in 2 here, I get um, oh yeah, this will work out, right? My brain just died on me. So here I'll have 10 plus 4, so 14 over negative 6, so negative 7, so 14 over negative 7, which is minus 2. So that works out, right? So sometimes when you're picking a point, try to pick a point so your fraction's not bad. Okay. All right. And then the last thing I want to do is just draw an example of a reflection. So here, if I have this, and let's pretend I have some function here. And I'll make it 1 to 1. Nope, that's not being 1 to 1. There, that's a 1 to 1 function. And let's pretend we have, so here, if I have this line right here, which is y equals x, and I have this as my function value, my inverse, which I guess I'll just do in this orange, right? It's just a reflection across this line, so it comes out, it comes back in, it goes back out, okay? And so it's just a reflection across this line. So if it was here, it'd be here. If it was this distance, it'd be this distance. Okay. All right. Well, that's the end of the inverse section. I'll let you copy that. So yeah, so a couple key takeaways. You do the horizontal line test to see if it functions one-to-one, aka every every input gives unique output. So unique inputs give unique outputs, so they don't match ever. And then if it has an inverse, we can find it by doing the following steps, which is interchange that. And then the reason we develop inverse is that if I take a function, apply its inverse to it, I just get whatever element that was originally in that. And we'll do that later to solve lots of other equations, right?